Hello friends, today's question. Two spheres P and Q of equal radii have densities ρ1 and ρ2 respectively. The spheres are connected by a massless string and placed in liquids L1 and L2 of densities σ1 and σ2 and viscosity nu1 and nu2 respectively. They float in equilibrium with the sphere P in L1 and Q in L2 and the string is taut. If sphere P alone in L2 has a terminal velocity of Vp and Q alone in L1 has a terminal velocity of Vq, then so we have to find out first of all what is the relationship between the terminal velocity and their viscosities, and it is a basically multi-correct or it can be single correct also. So directly it's then nothing but the question is about the relationship between Vp and Vq, whether it is in the ratio of the viscosity or it is greater than less than equal to 0. So this is a basic figure. We have two liquids L1 and L2, and L1 we have a P and its density is given as σ1 ρ1 sorry, and L1 is a liquid with density σ1. Okay, so σ1 is the liquid density of L1, σ2 is the liquid density of L2, and we have P, that is sphere, which is having a density of ρ1, and we have Q, which is having a density of ρ2, and they are you can say, yeah, that's all. Their terminal velocities are also given. For P it is given as Vp, and for Q it is given as Vq, and we have their respective viscosity is also given. So L1 is having a viscosity of nu1 and L2 is having a viscosity of n2. So these are the basic information that is given to us, and in the question it is directly mentioned that we have to use the formula for the terminal velocity. Okay. So let us analyze. We have two liquids separate, and let us analyze the terminal velocity for each liquid. So we say terminal velocity of each liquid. So we know that as soon as a body which is traveling through a viscous liquid reaches its terminal velocity, then the drag forces due to the viscosity is balanced by the net gravitational force as well as the buoyant force. Okay. So you can say that when the sphere reaches the terminal velocity, in the viscous fluid, the drag forces due to viscosity is balanced by the net gravitational and buoyant forces. And the net gravitational and buoyant forces. So in order to find out the drag forces, we can make use of the Stokes law. Okay. So let us find out the drag forces. We say according to Stokes law, the drag force, let us call that Fd, will be equal to, we have 6 pi nu r multiplied by v, and v is our terminal velocity, v is our terminal velocity, r is the radius of the sphere, radius of sphere, and nu is the viscosity of the liquid. Nu is the viscosity of liquid. Now this is, you can see, general formula. Now this, we are going to modify this formula specifically for now for sphere P as well as now for sphere Q. So we start with sphere P. So we say for sphere P in liquid L1. So we can write the gravitational force for sphere P. So let us draw a rough diagram for sphere P. So this is our sphere P, and it is having a terminal velocity of Vp. Yeah, it is given as Vp, and the downward direction, it is going to have mpg, and the buoyant forces will be acting in upward direction. Let us call that as FBP. Okay, so therefore the gravitational force will be equal to mp multiplied by g. Okay, we start with the gravitational force. So we say gravitational force, and we call that Fg for P, and that will be equal to mp multiplied by g, where mp is the mass of sphere P, mp is mass of sphere P, and we can just modify this particular formula, that now Fgp, let me write it again, Fgp will be equal to mp, that is mass of P multiplied by acceleration due to gravity, that is g, and we can write the mass will be equal to density of P multiplied by volume of P, and this is multiplied by g. And density of we can say sphere P, that is rho P, it is given as rho 1, and Vp is the volume of sphere P, and that will be equal to 4 by 3 pi r cube, because r is given as radius. Therefore we can write that our Fgp will be equal to, we have, it has 4 by 3 pi r cube multiplied by rho 1 multiplied by g. Okay. So this is our gravitational force. Next we write the buoyant force. Buoyant force, and we call this FBP, and that will be equal to density of the liquid, which is given as sigma 1 multiplied by volume of the sphere, which we have taken as Vp, and multiplied by g. Okay. So let me mention here that Vp is volume of sphere P. So Vp we already know, so we can write the equation that our FBP will be equal to, volume is our 4 by 3 pi r cube multiplied by sigma 1 multiplied by G. So this is our, you can say, buoyant force FBP. And now we can write the drag force also, equation for drag force rather. So we can say the drag force at terminal velocity Vp, at terminal velocity Vp, and let us call that as Fd, or P will be equal to 6 pi nu 1 r multiplied by Vp. So we can write the equation that at the terminal forces, at terminal velocity all the forces are balanced. So we can say at terminal velocity all forces are balanced. Therefore, we can write the equation that our drag force FDP will be equal to gravitational force FGP minus the buoyant force FBP. We substitute the respective values. FDP was our 6 pi nu 1 r multiplied by Vp, and our your gravitational was 4 by 3, and we have here, okay, in this case the 4 by 3 in the buoyant force as well as in gravitational force will be common, 4 by 3 pi r cube as well as G. Okay, so we take it as common, 4 by 3 pi r cube, and we have rho 1 minus sigma 1 multiplied by G. So pi goes with pi, this cancel here with square, and this comes as 2 and this comes as 3. So we can write that our terminal velocity Vp will be equal to, this becomes our 2 r square sigma 1 minus rho 1 multiplied by G, and this becomes divided by, and this will be our 9 and nu 1. So this is our terminal velocity of sphere P. Now we are going to do the similar analysis for our sphere Q also. For sphere Q in liquid L2. So let us start with gravitational force. We have gravitational force and we call that FGQ, which will be equal to, we can write it directly now, that will be equal to 4 by 3 pi r cube, and that will multiply with its density and multiply by G. Similarly, we can write the buoyant force and we call that as FBQ, and that will be equal to our 4 by 3 pi r cube, and density of the liquid is sigma 2 multiplied by G. And the last is our drag force. So we write that the drag force at terminal velocity VQ. At terminal velocity VQ, and we call that as FD for Q, and that will be coming equal to 6 pi nu 2, and we have R and VQ. Similarly, we are going to find out, or we can say write the equation for that at terminal velocity all the forces are balanced. At terminal velocity forces are balanced. So we can write our F drag Q will be equal to FGQ minus FBQ. We substitute the respective values, and that will be 6 pi nu 2 R VQ, and this have we have 4 by 3 pi r cube rho 2 minus sigma 2 and multiply by G. Pi goes with pi. This gives us square, and here we have 2 and here we have 3. So I can say my VQ will be equal to, we have here 2 R square 2 minus 2 divided by G, and this becomes 9 nu 2. So if we divide Vp by Vq, ratio of Vp by Vq, so we substitute value of Vp, and our Vp was 2R square, and we have rho 1 sigma 1 G divided by 9 nu 1 divided by, and we have here 2R square sigma 2 minus rho 2 multiplied by G divided by 9 nu 2. 2R square G 9 cancels out, so we get from here Vp by Vq will be equal to sigma 1 minus sigma 2 divided by rho 2 minus sigma 2, and we get this as nu 2 divided by nu 1. This is the partial solution. Now we are going to use that the entire system is in equilibrium, because the answer that is given to us is only in the formation of Vp and their nu 1 and nu 2 respectively modulus terms. So it means we have to remove this particular term or solve this particular term. So we are going to use that entire system is floating in equilibrium, as it mentioned the you can say question itself. It is mentioned that they float in equilibrium. So we are going to make use of this statement, which states that as the system is floating in equilibrium. So let us discuss first of all for sphere P. So this is a sphere P, and in the downward direction it is going to have its weight, which we call as a gravitational, that is FGP, and also it is connected by a thread, so there will be a tension T, and in the upward direction it is going to have a buoyant force, that is FBP. So we can write the equation that for sphere P, we can say that our FBP will be equal to FGP plus T. Okay, and for similarly we can draw for sphere Q also. So this is our sphere Q. In the downward direction we are going to have FGQ, and in the upward direction we are going to have a tension T, and next we are going to have the buoyant force Q. So we can write that for sphere Q, we can say, we can directly write it as T plus, let me write in this formation, FGQ is equal to T plus FBQ. From this equation we can write that our T will be equal to FBP minus FGP, and from the other side we can write our T will be equal to FGQ minus FBQ. So which basically tells us that our FBP minus FGP will be equal to FGQ minus FBQ. It means all the forces of P will be equal to the respective forces of Q with their direction, that are plus minus signs. Now we simply substitute the values for FBP, that is for sphere P, and we can write that this will be equal to sigma 1 volume of P and multiply by G minus FGP is our rho 1 multiply by VP multiply by G, and next is our Q. Similarly for other side also we can write our rho 2, and we have Q multiply by G minus, and FBQ, that's the buoyant force, will equal to sigma 2, and we have VQ multiply by G. And where VP and VQ are the respective volumes, but in the question itself it is mentioned that they are having equal radii. Okay, so we can say that volume of P will be equal to volume of Q, which is equal to 4 by 3 pi r cube. Therefore we can cancel the, you can say, common terms. G goes out throughout, and because of this expression the respective velocities will be also cancelled out. Okay, therefore we are going to get the equation that states that sigma 1 minus rho 1 is equal to rho 2 minus sigma 2. Okay, and we can just tweak it also. We can write that sigma 1 plus sigma 2 is equal to rho 2 plus rho 1. Okay. And we can also write it otherwise also. So you can say this is equal to minus of sigma 2 minus rho 2. In either way we can just, you can say, just it's a manipulation. And we are given, or we can say we derived the ratio of our, we can say, the VP by VQ. Yeah, you can say, but VP and VQ is our sigma 1 minus, rho 1 minus sigma 1 divided by rho 2 minus sigma 2 multiply by, we have this nu 2 divided by nu 1. So from this particular expression, this as well as this, we can use any of permutation and combination, and we can write this will be equal to minus of nu2 divided by nu1, and this is going to give us the final answer that the respective modulus of the ratio will be equal to our n2 by n1. So therefore we can say that our option number B is the correct option. So we can say from here that our option B is correct. And for the second part, or we can say second option, if you have to check whether it is correct or not, so it states that Vp product of the phase velocity of Vp and Vq is greater than 0, or product of the phase velocity of Vp and Vq is less than 0. And from the expression itself, these equations 1 and 2, and inclusive of this expression, let us call this equation 3. So we can say from equation 1, 2 and 3, we can say that Vp and Vq, that phase velocity of P and phase velocity of Q are opposite in sign. So if they are opposite in sign, obviously they are product. Therefore we can say the product of Vp and Vq will be always less than 0. Therefore Vp dot Vq is less than 0, and which is our option number D. Okay. So we can say option D is correct. Option D is correct. So this question was, you can say, interesting one, and which consists of, you can say, two liquids, and we are going to use the terminal velocity in both the liquids and find out the respective phase terminal velocity relationship. Okay, so this completes the question. Thank you.